Hi everyone, today I'd like to introduce you our research paper called Adaptive Issue Detection in Holistic Optimization of Distributed Data Streaming Systems. Streaming processing has become a critical part of enterprises, encompassing various spheres such as IoT, personalization, fraud detection, science, and other. Without a doubt, enterprise success lies in transforming instant data into valuable insights. Streaming processing is the evolution of TL-LT pipelines, while shift-left approach addresses main challenges in real-time processing. This approach has multiple benefits such as the efficiency of data processing is enhanced, continuous processing causes minimal delays, is compatible with traditional and analytical tasks, has better data quality, and faster innovation and data products. While this sounds very promising, further we will analyze potential drawbacks and suggest a change that will significantly improve the current design. First of all, let's analyze related works. In the previous research, we have introduced a competency model in streaming data architecture, while in this research, we have designed, developed, and evaluated the issue detection module in this architecture. The following research papers highlight the common issues in real-time processing, such as resource exhaustion, throughput decline, and latency spikes. Most of these issues are caused by performance bottlenecks. So the next research article analyzes network bottlenecks, computational bottlenecks, memory, input-output, downstream dependencies, and highlights root causes, how to evaluate and detect them. We have analyzed current anomaly detection methods. The existing approaches primarily rely on statistical techniques and predefined rule-based systems. So the mentioned research papers analyze these techniques in details. So the limitation of statistical method is that it assumes data follows a specific distribution and it depends on fixed manual thresholds that can't adapt to changing data patterns. So while the rule-based system requires a constant manual updates to stay relevant and inflexible, can't detect new unforeseen anomalies. To improve current anomaly detection flow, we have proposed our solution, designed and developed. It consists of the following modules. The most important module is ML Core. This ML Core is the heart of the system that performs real-time inference using a deployed model. We'll review it later. Also, anomaly database and control center. To build the ML module, we have analyzed the current approaches, the current architecture we can use. Among the mentioned, we decided to use transform-based autoencoder. Why? Because it's good at capturing long-range dependencies and complex correlations between hundreds of metrics simultaneously, and it's very stable. It is the preferred choice for modeling the holistic health of a complex distributed system despite its cost. To evaluate the system, we conducted multiple experiments. To prove the value of our system, we have compared it against two traditional baselines, static thresholding, just non-ML approach, and classical unsupervised model. Also, we have defined metric groups and KPIs that we use to analyze, evaluate the system. We have considered the following scenarios. The first one is to evaluate raw detection accuracy on standard public benchmarks to establish a performance baseline. The second one is to measure system throughput, end-to-end latency, and other resource utilization, so CPU, memory, and network utilization. The next one, to test the ability of the system to recover and adapt after a sudden permanent change in the underlying data distribution, and test the system to be able to track a slow change in data distribution without generating excessive false alarms. Let's see the results. First result. We have analyzed anomaly detection performance in public benchmarks. The public benchmarks, this is the mentioned one, NUM and Yahoo datasets. So here we can see that we compare with this isolation forest model and our transformer-based autoencoder model. We can say that basically, to some extent, it has a better result. On this slide, we can see the results for the scenario for performance and resource utilization at a sustained load, and for the next scenario, system resilience to abrupt drift. On this slide, we can see the results for the next scenario for resilience to gradual console drift. Here we can see performance degradation metrics, and we can see how transformer-based autoencoder adapts the dynamic thresholding. As a result, we can see that our proposed model demonstrates better performance, adaptivity, and resilience compared to traditional baselines. First of all, the transformer-based autoencoder achieves the higher F1 score, outperforming the static isolation forest with a strong balance of precision and recall. Then, regarding performance and scalability, we can see that it has high latency and resource utilization, but it definitely is suited for demanding environments. The throughput we achieved is like 22K events per second at the GUST 1, and latency remained in the limits. So the primary trade-off is the cost of superior accuracy and adaptability and the need of additional computational resources. Regarding the scenario for resilience and data drift, abrupt drift, when a sudden change was introduced, the static model F1 score dropped sharply. In contrast, the transformer-based autoencoder detected the shift and adapted to the new normal in just 20 minutes. So we're still in a good performance. And we can see results for gradual drift that it also has possessed a good result. In conclusion, this research tackled the key challenges of anomaly detection in dynamic, high-volume, distributed data streaming systems, where constant drift make traditional static monitoring methods ineffective. We showed that common approaches, such as fixed thresholding and non-adaptive machine learning models, like isolation forest, are essentially fragile. Their performance drops sharply with changing data distributions, causing a poor balance between too many false alarms and missed critical events. Our proposed solution, the adaptive issue detection model, effectively overcomes this limitation. So, thank you for your attention.